Ladies and gentlemen, our next speakers, we have Mr. Deep Wilson Aricatt, the Senior Machine Learning Engineer, and Mr. Anindya Chatterjee, Senior Machine Learning Engineer from Siemens. A quick info about Deep Wilson. Deep experienced senior computer vision engineer with demonstrated history of developing and deploying end-to-end deep learning projects focused on image enhancement and facial authentication. He has been working in the field of machine learning for almost 6+ years and has done extensive work on computer vision, image processing, classification, and object detection. He is an expert in developing MLOps solutions for various customers in fields like smart transportation, industrial manufacturing, and IoT, smart cities, etc. One of his expertise being able to develop custom deep learning models. He worked in various projects for Mumbai Metro, Times Now, and Matlab. A quick info about Anindya. He is a senior machine learning engineering and a certified data scientist from IIT Bangalore and has a work experience of 7+ years in banking, insurance, marketing, industrial automation, and subscription businesses. He has presented various topics on data science, machine learning, and time series in various forums. At Siemens, where he works to identify potential areas of AI implementation, converting business problems into AI data science problem, design the solution, and implement it. The areas of work are smart transportation, industrial manufacturing, and IoT, smart cities, etc. He is a seasoned engineer with hands-on experience in statistical modeling, machine learning, and deep learning models. Well, the topic for today is chaos engineering for artificial intelligence using MLOps approach.
Good afternoon, everyone. My name is Anindya Chatterjee, and I work as a senior machine learning engineer for Siemens. So today we are here to present on the topic chaos engineering for artificial intelligence using MLOps. And I have with me my colleague Deep, and we are both going to present this session today. So this is what the agenda for today looks like. So we're going to talk about what chaos engineering is. We're going to talk about what are the computer vision tasks that we are performing in the industry right now, and how are they being performed right now. We're going to talk about uncertainty in images. We're going to talk about what is adversarial perturbation, what is a robust model, and what is chaos, and how can we introduce chaos in our models to make our models more robust. We're going to talk about how we can track experiments using MLOps and how we can combine chaos engineering, uncertainty, adversarial perturbations, and MLOps and kind of experiment using that. So this is what the agenda for today looks like. So without wasting any more time, I'll just start off with the presentation. So what exactly is chaos engineering? So chaos engineering is a discipline of experimenting on distributed systems in order to build confidence in the system's capability to withstand turbulent behaviors in production. Right? So to do that, this is a concept which has been developed or which Netflix has come up with, and they have a set of tools which they have, and they call it as a Simian army. Right. So Simian army is nothing but a set of tools which runs and it tests the chaos and it causes chaos in your system and in your production environment, and tries to see how the application or how the systems reacts to it. So the most basic tools which we have is something called as a chaos monkey. So it kind of kills random instances. Then you have a chaos gorilla and chaos kongs, which randomly kills zones and regions. So here, when I'm talking about instances, zones and regions, I'm specifically referring to AWS regions and zones. Then there is something called as a Latency Monkey, which will increase your network latency and make sure your system doesn't, and make sure it tests kind of if your system is behaving fine or not. Then we have Chaos Doctor, Chaos Janitor, which fixes up unhealthy resources and then cleans up unused resources as well. So this is how the Simian army, or the set of tools which helps to introduce chaos, and they kind of tests the systems against these chaos. So there's usually two-step chaos. One is simulate what are the things can go wrong, and find things that are different. So So how can we incorporate chaos, and what would be chaos when when we talk about computer vision tasks in particularly about computer vision tasks? So let's try to understand what are the current computer vision tasks that has been followed in the industry right now. So currently the tasks that are being followed primarily are on the areas of image classification, quantization, object detection, and recognition systems, right? But a very few and a very limited number of work is being done on something called as adversarial training, which we are going to focus primarily today and try to see how adversarial training can be used in order to make your models more robust, right? So to give you a brief understanding of what exactly are these tasks and how this task looks like, we're going to talk about the usual computer vision tasks and try to give you a visual about how each of them looks like. So these are the most common tasks that we kind of perform on images, right? So there's something called as classification, where you may have a single class, a binary class, or a multi-class classification, where you have objects of different class. Like for example, in this image, we have an image of a cat, right? So you may be doing an image classification where you're classifying cats and dogs, right? So that becomes a classification problem where it will just classify and say whether it belongs to class A or it belongs to class B. Then you have something called a segmentation problem. Now segmentation problem can be split into two parts, which here is mentioned here as a semantic segmentation, and then you have the instance segmentation. So these are the segmentation problem, where you can understand from semantic segmentation that basically all the pixel of the particular image needs to be associated to a certain class, and even if a certain object, even if a cat appears twice, they will all both be from one class, right? But in kind of instance segmentation, as you can see, if it belongs to the same object, the second dog will belong to a different class than the first dog, right? And then there is something called as an object detection, where you're kind of detecting the object in it, which would be like a very common task which we're performing nowadays due to COVID scenarios, which we will be doing a PPE kit detection, or the person, or you kind of do whether the person is wearing a mask or not. So all these tasks can be accomplished using object detection. Then you have something called as a classification and localization, where you not only classify whether it's a cat or a dog, but you also try to localize the position of the cat. So this kinds of puts into account something called as attention, where you're kind of putting your attention on a certain set of pixels in that particular image, which actually makes sense to that particular problem statement, right? Now, what is uncertainty when we talk about image segmentation? So as I mentioned what image segmentation is, now let's try to understand what it would be an uncertainty in image segmentation problem. So as you can see here, let's try to understand this kind of a problem where let's say you have a self-driving car application, and you're supposed to segment the roads from the footpaths that are there, right? And if there is an uncertainty, or if there is a misclassification between the road and the footpath, that may lead to a major accident for a self-driving car application, right? So as you can see that this is what an uncertainty looks like. If you see the last two columns right here, so these are the mainly what uncertainty looks like. And there are basic and an overview at a high level. There are two types of uncertainty. One is the aleatoric and epistemic uncertainty, other two types, right? A little more details about the two uncertainty we'll be talking about in the later slides, right? So for now, as you can see, there is an image, there is a truth, and there is a prediction. So the truth is basically the actual classes that each and every pixel belongs to, and the prediction are what classes are my model predicting that particular pixel to be, right? And if there is a difference between these two, that causes an uncertainty in that particular model. Now the uncertainty can be split in two parts, aleatoric and epistemic, which we'll cover in a later point of time. Now, why do we need, and what is the use that we need uncertainty, or what is the use that we have to detect uncertainty in images, right? Let's take an example of an image segmentation problem where we are kind of segmenting MRI scan for brain tumors, right? So these kind of problems, right? Just estimating, or as we know, right, that the deep learning models kind of produce a point estimate, which is often not correctly interpreted as a probability or model confidence, right? So in order to, so that actually cannot explain the model's confidence, and leads to generalization issues, and also you cannot predict the confidence, or you cannot say that the model is confident that this area belongs to that this is the particular proper segmentation of the model, right? For that, if you can introduce a sort of an uncertainty to your model, or you can view the uncertainty in your image segmentation kind of a problem, that helps a lot, because that is the area where you can have a human in the loop for your use case. In this example, a doctor, in which you may express that there is an ambiguity and ask experts for further inspection or correction. So this is the main reason why you need an uncertainty image, because that may lead to, because other that is and this is mainly the reason why we are gaining much more confidence in prediction systems nowadays when it comes to medical imaging. So as I was talking about the types of uncertainty, so let's go ahead and quickly understand what are the types of uncertainty here. So broadly, uncertainty can be classified into two broad classes. One is the aleatoric and epistemic uncertainty, right? So aleatoric uncertainty is something which is caused by uncertainty in the data. Now, by uncertainty in the data, that may lead to inherent stochasticity in the data. So stochasticity is nothing but its randomness, or its noise, or its irregularity in the data, which may occur due to class overlap, it may occur due to label noises, or it may occur due to homoscedastic and heteroscedastic noise. That means noise with constant variance, or noise with variable variance, right? And these leads to high uncertainty in the prediction. Now, aleatoric uncertainty, since it is a data uncertainty, it cannot be reduced if you collect more and more data to solve the problem, right? So aleatoric uncertainty can only be removed or reduced if you can observe all explanatory variables with a greater precision, right? On the other hand, there is epistemic uncertainty, which is known as a model uncertainty, which is a consequence maybe of a insufficient learning, or maybe not proper hyperparameter tuning, or maybe due to finite set of data, and that leads to epistemic uncertainty. Now, since this is an uncertainty which is a model level uncertainty, this can be reduced with proper training, or by increasing the size of the training data set. Now, as of now, we are talking about uncertainty when it comes to image segmentation as a problem, right? Now, let's talk about uncertainty when it comes to image classification, right? So let's take MNIST dataset, for example, where we're trying to classify images of numbers into its proper classes, right? So as you can see here, that the network, or the neural network, doesn't give the proper output. The first image on the top left looks like an 8 to the human eye, but the network sees it as a 3. And the same goes for the other as well. So this is something which is also called as the uncertainty in image classification, where the model or the network is not able to classify the images into its correct classes properly, right? Now, how do we exploit uncertainty and create chaos for our model, right? So there are multiple attacks. So there are various types of attacks which we call as adversarial attacks, and these are the attacks that can be happening to your model at any time right now. So in sense of a neural network, keeping neural networks in mind, we have broadly classified it into 6 categories of location specific, knowledge specific, and intent specific attacks. So location specific attacks are something which happens either at training or at inference time. Knowledge specific attacks is that how much knowledge does the attacker or the attack has on the particular model. So it can be a white box or a black box attack. And there is intent specific attacks. So if in terms of if it can be a targeted or non-targeted attack based on whether it wants to target a specific class of classification, or it just wants to target misclassification and doesn't care about what is the class that it wants to target, right? So very simply, just trying to explain what each is. So training attack is something where we increase the number of misclassified samples at test time by injecting a small fraction of carefully designed adversarial samples into the training data. That would be the training attack, and the same that we do it on at inference time would be called as an inference attack. Now, the white box attack and black box attack is actually quite interesting to see. Is that because the attacker may so as we know that deep learning models would be a black box, right? So, but a white box attack would have complete knowledge of the targeted model, including its hyperparameters, the training methods, the parameter values, as well as the training data, and exploit all these information to attack. So that is what we call as a white box attack. And black box attack will have no information about the model that it's attacking, but it may use the context or historical information to infer model vulnerability and may attack, and that may lead to a black box attack. For targeted and non-targeted attack, the adversary tries to force the output and specifically target a certain class, whereas non-targeted attack doesn't specifically target a certain class, but as long as it doesn't predict the correct label. Now, what do we mean by adversarial perturbations? Now let's try to understand what adversarial perturbations is and how does it affect the neural network. So here, as you can see, we see the two person, and what we are trying to do is that we are trying to understand the age, and we are trying to understand the gender of the two person who are standing here, right? So as you can see, the first person that it is kind of detecting, it's saying that okay, the age is lies between 20 and 32, and it's predicting that it's male with a 82% confidence. And whereas the second one, it's predicting that it's the age ranges between 22 and 34, but the prediction of it's being a male or a female, the confidence is 98%. So as you can see, the first image doesn't the first person doesn't have a high confidence interval. The reason it being that is that it holds a picture which has other images or other person's face in it. So that is the reason. This is one type of adversarial perturbation, that it's confusing the model as to what is the actual gender of this particular person is. Now, so what do we generally do in our training and evaluation process when we are building deep learning systems? Are that we kind of train or retrain our model until and unless we reach a certain accuracy, which we have defined as our state of the art. And if we have achieved that accuracy, we say that okay, we have reached a state of the art network, and if not, we go and keep on retuning or fine tuning our hyperparameters based on our requirements. But does this alone declare the model as robust, or are these model actually robust against the adversaries attacks or the adversarial attacks that we are speaking about earlier? Now let's try to understand how we can actually when we are building an AI system, or when we are building a deep learning or a vision based system, how do we actually keep in mind the chaos attacks, and how we can actually build a backlog and try to plan our adversarial attacks and plan our model in a similar way. So the best way to do is to try to brainstorm and determine what could go wrong in an AI systems from model as well as data perspective, because that will clear up both your aleatoric and epistemic uncertainty. Then you could convert the backlogs into your chaos engineering experiments, and then you may learn and write automated chaos experiments, and then maybe turn your chaos experiments and use your data that you have generated through your chaos experiments to retrain and test your AI model. So only by doing this are you making your model robust against adversarial attacks. Now let's try to understand how do we exploit uncertainty and make our models more robust. So as of now, we are talking about only that, okay, we should make our models robust against adversaries, but how do we actually do it, right? Let's go and understand this. But before we go there, let us first try to understand what a general ML ops or a machine learning pipeline with a MLOps actually look like, right? So as you can see in the section which is highlighted in red, right, this is the area which is the actual our actual machine learning pipeline, which consists of a data extraction, validation, and preparation frameworks. Then you have the model training, evaluation phase, and then you have a model validation, and then you store the model objects and which you are using for model inferencing. And you maybe have a Amazon CloudWatch, which is doing a performance monitoring of your models. And then based on your demand or on a schedule of 3 or 6 months, you kind of retraining a model based on a trigger. So this is a very generic overview of how the MLOps pipeline look like. Now, let's try to understand how do we use uncertainty and create data level chaos and try to understand the weakness of a model. Now, let's try to understand this particular image that I'm talking about here. So this is a panda, right? So on the left hand side, and if you pass this image to a certain image classifier, it will classify panda, say for example, with a 70% accuracy. But when you add a certain noise to the data, it kinds of completely confuses the model, and this is not able to detect a panda when you put it in a model, right? But to the human eye, it still looks like a panda, and we are not able to understand whether there has been a difference, right? So that brings me to my point, right? That however human perceives images and how machine perceive images is completely different. So even for the human eye, if it doesn't look like a problem, it may still be a problem to the machine. And that is the reason we have to make sure that our models are robust and tries to understand these kind of chaos, right? So what we are going to do here is we're going to take the same data set, and we are going to try to understand that how we can create fake samples of it, right? So as you can see here, this is the trained model. Now let's take an example of of what we have been talking here, that this is our trained model, which would be our model, which we are going to deliver to a customer, or we are building a product of it, or whatever it is. So this is our trained model, which in this case, let's take into account, this is a classification problem. Now, what we are going to do is, we say that we have done a VG16 or a RESTnet, and we have performed and we have used that as a backbone of our application, and we have done some sort of transfer learning and build a model, which is our classification system. Now, what are we going to do it as? We are going to introduce something which is called as the chaos monkey for our system, right? So the chaos monkey for our system would be a generator which will generate from a noise, which will generate fake samples of data, right? So this is a fake sample of data that we are generating. So this follows a traditional generative adversarial network architecture, where from a noise we are trying to generate fake samples of the data, and there is a discriminator which is strong enough to discriminate whether the sample is actually a fake or a real sample. So from the MNIC data set, there comes the real sample, and from the fake generator, we get the sample, we get a fake sample, and the discriminator is strong enough to identify what is actually the real and the fake sample. And based on this particular label of the fake and the real, we will be pushing these images into our image classification network to kind of understand how do we stand on in terms of adversarial. So this is basically creating adversarial samples or adversarial perturbations of our data, and then coming up and trying to test our model against these attacks. So this is a simple case where this generator or this GANs network becomes our chaos monkey for our image classification system. Now, what we are trying to do is that how do we track this adversarial image generation using MLOps? So this, as I said, that this is the particular piece of our application, which is the chaos monkey in our case. And this tracking of the generation of these adversarial images becomes very important, and we need to track this particular through experimentation, and we can track this particular model using something called as the ML flow. Now, to talk you through the ML flow pipeline of it, I have Deep with me. So I would like Deep to take over from here. Deep, the stage is all yours.
Thank you, Anindya. Yeah, so moving ahead, I'll be talking about how we can use MLOps to track your experimentation and make sure that you can push it into production seamlessly. So MLOps is a very nascent field. So there would be inconsistencies in the definitions. So there are no hard-coded definitions as such, nor there are much official nomenclature. But it would be safe to define it in the following way. So to develop and deploy machine learning systems in an organized way. So why MLOps? So as the number of modules or the scale grows, your complexity also increases proportionally. So automation helps us in faster deployment of these deployment pipelines from staging to production. And it also results in ease of deployment. So moving on to the next slide, we are going to be talking about ML Flow, which is an open source tool that we would be using to track our MLOps. And as you see on the screen, these are some of the specific stages that we would be discussing going ahead. So if you notice, there is an ML Flow tracking server, which helps us to track our hyperparameters, metrics. It helps us to log our artifacts, such as our models, or you want to log some metadata, or you want to save your models. All of these can be done with your tracking server. And going ahead, we have a model registry. So once you train your model, you want to make sure that it can be pushed to production. And if there is a need that comes up later on and you want to move it to the archive section, you can do that too as well. So in that case, we have the model registry from MLflow, which can help us to do the same. And then after that, you can deploy your model and pass it on to other downstream tasks, such as serving it as a REST API, or maybe carry ahead a more automated jobs. So MLflow can help us in all these sections. So moving on to the next slide. So we're going to discuss about some stages of MLOps pipeline. So starting with the scope. So like I said, it's a holistic requirement. So we're not completely dealing only with the deployment. We want to discuss right from the collection of the data up till the deployment of the model. So to talk about the scope, once we begin a project, we can always discuss requirements and consider the clients that do not have a tech background. And going ahead, we have the data collection and the EDA. So most of the times, machine learning engineers tend to ignore these factors especially when it comes to data. So one of the most prevalent problems that are there is when there are manual data labeling that is required, and when the data labelers are not in sync, you result in a data set that is not good enough for the model. So we want to make sure that when we collect your data, the data set that if it has to be labeled manually, you want to ensure that the data labelers are on the same page when it comes to how we should be labeling your data. And domain knowledge plays an important role over here. So depending on the project or the background nature of the project that you're going to be working on. And like I said, consistent labeling between individual data labelers is a very important factor that you need to consider. Along with it, we need to ensure that we are covering outliers when it comes to our data sets, and also to ensure the privacy and the security if personal data of the client is involved. So moving ahead to the next stage, it's the previous slide. Yeah, so the next stage is about a model training or experiment tracking. So here, once you train your model, you as a machine learning engineer, you should be able to justify the actions that or the predictions that your models make. And for this purpose, we should make use of model interpretability tools. And along with it, you want to also justify the particular model architecture. You want to make sure that your edge computing requirements are satisfied when it comes to your model architecture. MLflow helps us to track our experiments and ensure that we're using the right set of techniques to train our models. So moving on to the next slide. Yeah, so here we have the next stage, that is model versioning. So like I said, once you train your model, at times you want to make sure that you want to test your model predictions and then push it to production. So MLflow gives you a CI/CD type of workflow pattern wherein you can seamlessly push your models from staging to production. And over time, as your model degrades, as new data comes along, you might want to push back your models to the archived section. You want to push it back to the staging section. So if you can see on my screen, MLflow gives you a UI wherein you can do the pushing from the model from staging to production very easily. So if you notice on the left side, I have created my new model and I name my model, give it a name. And then once I register my model under MLflow, if you notice on the right side, you can see the section called as staging and production. So once you give your version name and then you can push it to staging. On the right side, if you notice, there's a drop-down menu wherein you can push it from staging to production or vice versa. So moving on to the next slide. So once your model in deployment, you want to make sure that you're monitoring it so that you can get feedback from the client or from the model itself, and make sure that your model is not degrading over time. And in case if it degrades, it's time to retrain your models. That's why you push it back to staging and make sure that you carry on the workflow as mentioned in the previous slides. So moving on to the next slide. So what is MLflow? It's an open source platform, and it is framework agnostic. So you can use this tool with any of your machine learning frameworks like TensorFlow, PyTorch, sklearn, etc. So it mainly deals with four primary functions. So like I said, it can be used to track your experiments. So that comes under MLflow tracking. And next, you can use it to share your projects with your co-workers. So most of the time, if I have trained my model, I have finished my project, and now I want to hand it over to my colleague, and I want to make sure that he trains it on a new data set. So I can always share my data in a very organized way. And that's where MLflow helps us with reusable and reproducible form of sharing your work with other data scientists. And the third function would be a deployment of your models, like I explained earlier. And the fourth factor or the function that MLflow helps us with is with having an organized way of storing your models in form of a model registry, where you can always carry out transitioning processes later on in your pipeline. So moving on to the next slide. So right now on the screen, as you can see, I have two examples. So on the upper half, I have an example of an MLflow project file. So an MLflow project file is a text file which follows YAML convention. And if you can see, I have my name of the project. I have my Conda environment, part to the Conda environment, which is in a YAML format. And under the entry points, I have my different hyperparameters that I have used to train my experiment or model. So if I want to share it with any of my colleagues later on, I simply share my MLflow project file. And if you notice, there is a command line wherein I can pass on the train command, which my colleague can use to re-experiment or retry my experiment with his or her data set. So on the bottom half, you can see that there is an MLflow run command which the user can use to retrain my experiment, and he has the flexibility of playing around with the different hyperparameters. And moving on to the next slide. So this is how you can activate MLflow in your code. So whichever framework, since it's framework agnostic, or you can use it with any of your frameworks. MLflow helps us set up a local URL wherein you get a UI by which you can track your experiments. So if you notice, the run command over here is MLflow server. And then if you notice, there's a backend store URI wherein I can link my MLflow to any of the database of my choice. So I would prefer linking it to a Postgres DB. And along with that, I give my host point, and then I set my port, and I have my MLflow server up and running within a few seconds. So once you get your tracking URL, you can go to your local host, and you will already have a UI which is going to be beneficial when it comes to tracking. And I'll be showing ahead some screenshots of my UI which I use to retrain my model. So moving on to the next slide. Yeah, so here you have the MLflow UI. So like you can see on the left-hand side, I have a list of my projects that I'm working on. And right now I have linked it to my local Postgres DB. So I have all of this work stored on my laptop. And if you notice on the right-hand side, you can always, you have your different trials of your experiments that you have. And you can always use the filter command to filter it by any metric of your choice, or maybe you want to have the model which has the best accuracy. You can always go ahead and use the filter section to get the best model. And moving on to the next slide. Yeah, so this is how we can use MLflow to track our experiments. We have a UI wherein you can choose your metric that you want to track, and you have a visual, summary board that you have that you can track your experiments with. So here MLflow helps us a lot. So moving on to the next slide. So to conclude, as we know that AI and machine learning companies work very hard to avoid costly failures. But for complex AI models, a better approach is to ensure that you train them, and you make sure that you're dealing with the uncertainties that you think can come ahead in production. And we use chaos engineering, and we estimate model uncertainty so that we can proactively hunt for such weaknesses in our AI systems. So in our case, we had something like an image classification, and all of this we can ensure that this happens before it triggers a crisis. So for machine learning and AI, data is very important. And in our talk, we have explained how to use MLflow for your MLOps pipeline and to introduce data level chaos affecting model confidence. And we go ahead and use the same data to train the models and deploy a robust model to production. So that's it. Thank you for taking time to attend our session. And a huge shout out to the DevOps Summit India team. Thank you.
Thank you everyone for joining.